Good afternoon, ladies and gentlemen. I'm Peter Goddard, Director of the Institute for Advanced Study. It's my pleasure to welcome you here this afternoon to this first AMIAS lecture. AMIAS is an acronym for the Association of Members of the Institute for Advanced Study, who are holding their annual meeting here today. And our speaker today is Peter Galison, and there could be no better person to give this first AMIAS lecture, for his interests and research span just about the whole range of the work of the Institute. Peter is an historian of science, much of whose work explores the complex interaction between the three principal subcultures of 20th century physics: experimentation, instrumentation, and theory. Peter's books, including Big Science, The Growth of Large-Scale Research, and Einstein's Clocks, Poincaré's Maps, and his films on the development of the hydrogen bomb and on secrecy have reached a very wide audience. Peter took his bachelor's degree from Harvard, a master's degree in history and philosophy of science from the University of Cambridge, and a PhD in both physics and the history of science from Harvard in 1983. He's been a junior fellow of the Society of Fellows at Harvard from 1980 to 1983, on the faculty of Stanford University from 1982 to 1992, professor of the history of science and professor of physics at Harvard from 1992 to 2006, when he became Joseph Pellegrino University Professor in the history of science and physics at Harvard University. Peter was a member in our School of Social Science from 1994 to 1995, and he was a trustee of the Institute, nominated by the School of Social Science from 2004 to 2009. Amongst very many other distinctions, Peter was awarded a MacArthur Foundation Fellowship in 1997, and in 1999 received the Max Planck and Humboldt Stiftung Prize. At the end of his talk, there'll be an opportunity for questions, and following that, there will be a reception in Ford Hall. This evening, Peter's title is Objectivity, the Limits of Scientific Sight. Thank you.
Thank you, Peter, for the gracious introduction and also for all that you do and have continued to do for the Institute, and to colleagues and members and past members and AMIAS organization who love this place as much as I do. I'm very grateful to all of you for making this institution what it is. So I'm honored to be here in support of AMIAS. Today I'd like to talk about objectivity. Now, it's easy to think of objectivity as simply identical to science. That is to say, how could you have science without objectivity or objectivity without science? What I want to do is to historicize the idea of objectivity and to think about science as having virtues, something like the way we understand ethics, where virtues don't always pull in the same direction. We know very well that something could be equable but not just, but we're less aware sometimes of recognizing that the things we want in science, precision, accuracy, pedagogical utility, or objectivity, might actually be under tension at different times. And what I'd like to do is to go through some of the stages of our thinking about objectivity in the sciences, putting aside some of the issues of objectivity that come up in other domains. I'm not going to talk about newspaper objectivity. I'm not going to talk about the objectivity battles in the social sciences in the late 19th century, but to look primarily at the natural sciences and at images in particular. So the first point is that objectivity has a history. It has a history as a term. It's a 19th century term in a recognizable way that's continuous with the present. When people talked about objectivity or subjectivity or their Latin analogs earlier, they often meant exactly the opposite of what we mean about its relationship to the interior states and to the outside world. Objectivity is, as I mentioned, one virtue among others, and not to be identified in any too simple way with pedagogical utility, truth, precision, or accuracy. Objectivity can be studied through the visual, and that's what I propose to do today, to focus on atlases. Atlases are a continuous literature from the 17th, even earlier, 17th century, even earlier, but continue to the present. They're compendia, they're systematic compendia of the basic objects of what different sciences are. They're objects of almost anything you want. There are the atlases of clouds and atlases of hands and atlases of abnormal physiology and atlases of skulls and atlases of x-rays. And I want to look at them and to see what these atlases want from their depiction of the world. What do they think the working objects of science in different domains should be? Now, George Gamow used to put in his books little skull and crossbones next to things that he wanted you to be very cautious about. So here are my Gamovian warnings. This is not a history of all images in science. It's not a history of bar graphs and pie charts. It's not a history of, there are lots of images that this is not an account of. It's not a history of all kinds of objectivity. It's not a, CBS News objectivity or equal time or equal access objectivity. It's none of those things. It's meso rather than microhistorical. That is to say, it's not a study of a particular hospital in the 19th century in London and the arguments between the traditional doctors and the rising bourgeois doctors who argued about the use of the stethoscope. It's not that. It's about this pattern of ways of seeing, of forms of sight, of what would count as a valid depiction of natural objects in the world. The periodization that I want to use is layered rather than suddenly disjunctive. It's not a sort of Kuhnian picture of paradigm switches or where everything that used to happen is suddenly not understandable and we switch to another gestalt or religious conversion. It's not that. It's not a Foucauldian epistemic switch, but rather it's layers of techniques that get put on one on top of the other, so that as you begin, for instance, in the 18th century to characteristically use idealizations as the obvious way to depict, of course you want to depict the perfect skeleton, not one that's too thin or too fat or broken. That idea of perfecting and idealizing never entirely leaves scientific depiction. So when new forms, for instance, what we'll see is a form of objectivity or mechanical objectivity, as I'll describe it momentarily, it gets layered on. That is to say, then there becomes another way of depicting, but the old way never completely disappears, although it gets transmuted under the pressure of the new. I'll come back to this point, but I want to emphasize that this isn't the case that the form of sight characteristic of idealization in the 18th century, much more about this in a moment, is suddenly impossible in science, but rather new things are added and pressure the old ones. So these atlases look like this. They could be like Vesalius. They could be like this German atlas of clouds. They're atlases of typical X-rays by Rudolf Graschi, one of the great X-ray experts of the late 19th, early 20th century. There are thousands of these atlases. They refer to each other. Many of them are published by the same company. We'll put out atlases of X-rays and atlases of crystals and atlases of the hand and atlases of abnormal physiology and atlases of X-ray, of elementary particle pictures on cloud chambers and so on. So these are a genre that are recognized. It's one of the few genres, in fact, where the physicists learned and said they learned from the medical doctors. Physicists don't so much like to say that kind of thing, but here they did. And this centuries-long tradition of having these compendia of medical atlases became a model for what the physicists did to teach the next generation and each new group teach themselves how to recognize the basic working objects, to distinguish, for instance, one kind of particle from another. So this layered picture of periodization looks something like this, and I'm going to make cartoons of my own argument to try to make the clearest possible picture of the logic of what this book is about. The idealized depiction has as its base a metaphysical picture. That is to say, they wanted to capture the way a skeleton should be. Because they thought, why would you want to depict anything other than the right skeleton? Why would you want to have my skeleton or somebody else's skeleton there when you could have the skeleton that lay behind all skeletons in some way, the form of skeletons? In that sense, it was metaphysical, and the picture referred to something universal. And the scientific self, the appropriate kind of person to do this kind of work, to extract the perfect skeleton from all the imperfect ones that we have access to through our senses, is a kind of sage or genius. Around 1830, and these dates are artificially precise, they're just a gesture to an area, is to say that you have a procedural depiction. So your idea is not to use your genial self to depict what should be behind the things that you actually find, but actually you show a map that goes from the thing you find, the plant growing outside Wolfenson Hall on this day, onto the page with as minimum amount of interference as possible. There are particular objects, therefore, that are depicted. You can find this bone in that case in that museum. And the scientific self, then, is a kind of will-to-will-lessness, a kind of will to be transparent, to allow nature to speak through us, as you might expect a divine might say, in quieting desire to allow God to speak through us. This, though not theological in that sense, was a way of quieting our desires to improve nature and to allow nature as it stands in its particularity to be reproduced onto the page. And then a third layer begins in the 20th century, where you have the kind of person that is the appropriate scientist is now a trained expert, someone who is neither a mechanical machine tender, as the ideal would have been in the mid-late 19th century, and not the genius of the 18th century, but something else, someone who trained long enough and through that apprenticeship gained a way of classifying and making images that even if it couldn't be articulated, even if it wasn't even conscious sometimes why you would group a picture of a spectrum into one star category rather than another, it was reproducible so that we could learn how to classify in some intersubjective way, even if we couldn't explicitly make this into a rule that could be executed by a protocol or a machine. So again, continuing in the spirit of cartoons, this is a cartoon of the argument of this larger project, and much of this is work that I did with Lorraine Daston, who's from the Max Planck Institute. And so the first order picture is that in the 18th century, in each period, you have a kind of a quadruple of forms of analysis that you need to apply, and they're related to one another. The scientific self in the 18th century had as its ideal the sage. The image had this metaphysical status. The practice was one of massive intervention to extract the perfect entity, skull, shell, hand, whatever it was, out of all the particulars that you saw. And the ontology, that is to say what the object referred to by the image was a universal. It referred to no particular. Let me show you some examples. When Goethe talked about his Urpflanze, he said no particular animal can be used. Or at the bottom here you see his Urinsekten here, which didn't answer to any particular bug. There was no single bug that was the model for these images, and these images didn't call back to any particular insect or plant. Rather, these plant forms or insect forms were that which he thought lay behind. If you parted the curtains of experience, this was the furniture of the idealized heaven behind it. When Albinus in 1747 took his skeleton, they were obviously idealized, not just because you have a dancing skeleton in front of a white rhinoceros, but also because even within the depiction of the skeleton, he would say, so those things which were less perfect were mended in the figure to exhibit more perfect patterns. And that seemed obvious. Why would you depict a fat skeleton or a skeleton with a rib broken that he had suffered in a fight, or a skeleton that was too thin, or for the early part of the 18th century, any female skeleton at all? So the idea was to extract from the world around us something, first choose the best example, and then improve that. In the 18th century, you'll find sometimes a figure like this, William Cheselden's from Osteographia in 1733, and you say, oh, well, isn't this an example of somebody looking not to idealize, but to depict on this camera obscura? So you have this upside-down skeleton because of the inversion of the image will look right side up at the person drawing, and against the glass plate, he's drawing the image. And isn't that just a depiction of the individual as it is? Well, no, because what Cheselden did was he took this image and then he fixed it. He drew it and then he fixed the things that he thought were wrong, that made it depart from the ideal form that this individual happened to be aspiring to be. So what are the sight limits of this form of engagement with the world, this classification of the basic working objects? In ideal sight, and we'll call this form of sight ideal sight, you're aiming at the truth that exists behind appearances and individuality. We end up not seeing at all the imperfections and idiosyncrasies of individual objects. In a sense, they're filtered out by epistemology, by our strategy of how we gain and secure knowledge, by ontology, what we think these objects refer to, by the practices that we use to improve them and make them better, and to a kind of a self that's appropriate to do this. So not just anybody can make an atlas of skeletons. You want the appropriate kind of person who you can't train up to be a Goethe or an Albinus or a Cheselden. These are people who, by their nature, were supposed to have a vision of something behind appearances. I come back to my original schematic. Beginning in after the first third of the 19th century, you begin to have a different picture of the scientific self. Now people are not aspiring to be geniuses or sages. They want to be more like a worker who tends a mass production machine of bullets or forks. You don't want the creative imposition of the worker modifying each bullet as it comes out. You want the bullets to be as much as like one another as possible. And in the 19th century, for people like when Maxwell wanted to argue for the existence of God, he said, look, when we have bullets that are identical, you know that somebody made identical bullets, and if the molecules that we deal with are identical to one another, then there must be a creator. It's the weaponized argument for God. So the image then was mechanical. That is to say, above all, what you were trying to do was not to interfere. It was not to fix the skeleton, to mend it, to make it more perfect, in Albinus's words. It was to get your cotton-picking hands off of the image and to allow nature to be inscribed on the plate with a minimum of interference. The practice was therefore one of mechanical transfer. And in the 19th century, when they talked about the mechanical, it could be chemical. I mean, it didn't mean mechanical like pulleys and levers. It meant anything that was a procedural process that went from one thing to another. So the chemical development of the photographic plate was, for example, considered to be a mechanical process. When Benjamin talks about the age of mechanical reproducibility, he includes photography, and that's consistent with a very standard use of the term in the 19th century. And the ontology was one of individuals. That is to say, you're interested now in the particular skeleton, this particular person who died and left this particular skeleton, which we are depicting on the page, with all of its peculiarities. Let me give you some examples. And some of them are really, they're quite illustrative of the difficulty of this transition of valuing what was devalued and devaluing what was valued. It used to be that idealization was one of the great skills. That's why you wanted a Goethe or an Albinus, because they were capable of seeing behind the appearances. Now you don't want them in your laboratory. You want somebody who can keep their hands and their desires and their ambitions for theoretical unification off the image and allow nature to speak to the page, so to speak. So Funke in 1853 talked about images and the goal of the image maker as creating a faithful image, that we had to be conscientious, that we had to draw even the deceptions. This is highly moralized language, so language where the moral and the epistemological joined. The kind of person necessary for being an Albinus had to do with the genial aspect of a vision that he was able to muster. Here you want somebody who's committed to not interfering, and in that sense faithful to the image as it stands. Even the deceptions, he says. Well, what's an example of that? Well, in these images of crystals, Funke knew perfectly well that that these crystals were refracting one another, that there were optical illusions, essentially, of a crystal being bent. For instance, you stick your arm halfway into the bathtub and it looks like your arm is bent. And he said, draw that. Now, the idea of telling a Goethe or an Albinus or a Cheselden that they should draw optical deceptions or draw the yellowing around the edge of the slide because the chromatic aberration of the microscope would have been appalling. Why would you draw something that you knew to be false? And what Funke wanted, what the goal of mechanical objectivity was as a different form of sight, was to make yourself into a kind of continuation of the machine, to depict as faithfully as the microscope was doing, to be a continuation of the machine under other means to the page. So he drew these things. He drew the yellowing around the edges. He drew the refracting. He drew the distortion of the back end of a crystal as it crossed over to the front, and so on. This led to some mighty conflicts. For example, Golgi and Cajal shared the Nobel Prize in 1906 for a method of making microanatomical structures of the brain visible using silver. And they shared the stage at Stockholm, and they hated each other. And one of the reasons they hated each other was that they stood on opposite sides of this divide. Cajal said, I am going to depict things, and this is a slide from his Nobel Prize talk, and Cajal was sitting in the audience, and he records in his diary, he could barely contain himself. He was in such a rage over what Golgi was showing. And Golgi said, I've exactly prepared this according to nature. Well, you might say, well, he exactly prepared it according to nature. What could Cajal be complaining about? Well, prepare something according to nature meant, as artists reported very often, was simply saying that they drew it with the thing in front of them. If your model is sitting there, you drew according to nature. It doesn't mean that it's somehow a mechanical transformation of the model to the page. And that's not, the idea of a mechanical transformation to the page was not at all what Golgi wanted. In fact, he said, I've drawn this less complicated than in nature. It is a semi-schematic. So if you think that when he says it's prepared according to nature, that he means it's simply a transfer of what he's seeing to the page, then this looks like a complete contradiction. But it's not. He's looking at the slide, and he's fixing it for you. He's fixing it by what he knows to be the case, without going into details that these top structures are linked to the bottom structures. And Cajal believed that they're not. This is an argument over the independence of the neurons and its structure. And Golgi believed that the brain was one huge connected network, and there was nothing to be gained by thinking about these different layers as being semi-autonomous, but Cajal did. And Cajal was in a rage because Golgi was fixing things when they shouldn't be fixed. Cajal, when Golgi showed a glimpse of one of his figures, the one that I just showed you, it was artificially distorted and falsified in order to adopt it nolens volens to his capricious ideas. This is a clash between two forms of vision sharing the stage and winning the Nobel Prize. What Cajal saw as this capricious imposition, this falsification, was for Golgi using a lifetime of experience and understanding and insight into the structure of the brain and using it to clarify and to strip away the unnecessary faults of the system of observation and the sample that he was looking at. So he fixed it. Cajal, my competitors, seduced by the presumed necessity of continuous structure, they, Golgi and his sidekick Gerlach, then supposed the existence of an anastomotic net between the dendrites and the axis cylinders. Such a seduction could lure the weak-willed scientist away from true sight. And Cajal went on to write novels in which, the loyal scientist is seduced both epistemically and sexually away from his true sight. The goal of true-sightedness for Cajal was fundamental to all of his work, his advice to young scientists, his novels, his short stories, and his science. Another example, this time inside the same person, looking at this transition between different forms of sight, was a person named Sir Arthur Worthington, or later Sir, but Arthur Worthington, who studied the splashes of droplets, of milk drops and drops of mercury, drops of water, and was the first person to be able to record what they looked like. So he had this system, and using the principle Galileo talked about on the Leaning Tower, that things drop at the same speed, no matter what, at the same rate of acceleration on both sides of this. You have one side of this has a metal ball, and over here there's a little cup, and the cup is filled with whatever liquid you want to drop. And an electromagnet releases both of these arms at the same time, so they go down, and the metal ball drops. And if you had very good sight, you would be able to watch it fall, and you would see that the drop was exactly opposite in height the ball over here. When the ball got down to between these two balls over here. It completed a circuit, a spark went back and forth, and that spark could illuminate the scene for a very short amount of time, and you would have this bright flash, and using this sort of the sort of retinal image that leaves, we could see things, and he did. He saw these beautiful images that he drew on the left here, symmetric, perfect images of the drop as it impacted the surface and spread out with the rays over here. They're stunning images. And then a terrible thing happened. He began to hear about the new work that had been done by Mach and others. Mach photographed a shadow image of a bullet traveling faster than the speed of sound. It used all sorts of tremendous new discoveries that allowed people to make a kind of primitive flash photograph. And so he began to project the light on these images and to look at the shadow image that was left on photographic paper. And it looks good over here at 4.83 milliseconds over here, and then it gets bigger and gets bigger, and everything's nice, and then it starts to look wildly asymmetric. And it happens over and over again. There are no symmetric splashes. Everything that he's done in his whole life has been these beautiful pictures of symmetric flashes. And he then starts to repeat his old experiments, which he'd drawn like this from the retinal image of the splash to looking like this when he took a photograph of it. And he said, how could this have happened to me? And he began to sort of create a kind of psychological account about our desire to form symmetric images of the world. And he said, I actually sometimes drew a couple of pictures that were asymmetric, but I put them in my drawer because they weren't the true image. And so he sort of wrenched from one form of sight, from this idea that, of course, these things are symmetric, and correcting them almost without thinking, to giving a psychological account of how he could have gone astray and depicted things as symmetric when they were anything but. Here's another example. There's a long history of snowflake depiction. Everybody drew snowflakes. Kepler has snowflakes. Descartes has snowflakes. A long history of science. There are lots of pictures of snowflakes. And there are atlases of snowflakes, like there are atlases of falling drops and like there are atlases of everything else that we've talked about. So if you go through John Nettis's atlases of snowflakes, you see these beautiful hexagonally symmetric forms. They're really splendid, page after page after page after page. And then there's this one little critter over here, number 84, which I've blown up over here, which is incredibly asymmetric. And you look, and there's a footnote. Number 84 has got a footnote. And it says, actually, there are an infinite number of snowflakes that are asymmetric like this. But I'm not interested in them, and so I'm not going to depict them. So they're there. It's not as if it's physiologically impossible to see, but it didn't count as knowledge. It didn't count as what everyone knew, which was that snowflakes had a hexagonal symmetry. So in 1892, it was a mean winter in Berlin, Hellman and Neuhaus went out, and people have been trying to photograph snowflakes a lot, but you need a bright light because the paper's not that sensitive, the film's not that sensitive, and bright lights mean heat and snowflakes don't get along very well. It was really hard to photograph snowflakes. It wasn't until 1892 that anybody got a photomicroscopic picture of snowflake. And at first they said, one misses in photographed asymmetric flakes the absolute regularity and perfect symmetry. But in this departure, there are real pictures. Now, even some of the methods that were used had made it impossible to see these asymmetric snowflakes. Even if you weren't like Nettis and got rid of them with a footnote, one of the most famous depictors of snowflakes, he worked this way. He'd go out, he'd get his microscope, he'd get the slide good and cold but not too foggy, he'd look under it, he'd draw it, and he'd draw one of the arms, and then he'd give it to his wife, and his wife used hexagonal symmetry to make the rest of the snowflake. So they all, garantissimo, they were going to be hexagonally symmetric because that was the procedure that inevitably and inexorably led to a symmetric version because they knew that. It was a condition of possibility for being a snowflake. So in the 19th century, though, as this begins to break down and people like Neuhaus and Hellman begin to get used to this idea that the world isn't that symmetric sometimes as it was thought to be, they began to take a pride in being able to see the world as it was. And that pride, that sense that we now are capable of restraining ourselves against this overly geometrical idealization of the world, this search for confirming prior theories, that somehow we could see things truly, faithfully produce them on the page. Left over here of a sliced and dyed piece of tissue. And I've blown it up over here on the right. And he says, this is a matter of pride that I bring to you, that the fact that I've left these gaps in the slide, these white spaces here, where tissue has been lost in the process of the microtoming it and dyeing it, or that the cutting process has left these strands on the side. He said, I could have fixed that. I could have clipped them off and made it look all nice, but that wouldn't have been faithful. And you should believe this picture because on the face of it, the picture itself shows you its veracity. It shows you that it was as it appeared to me. I didn't fix it. I am an honest reporter. I am an extension of the machinery of reproduction of the basic working objects of nature, and for that reason, the picture bears witness in its asymmetric, so to speak, in its imperfections. It shows the finitude and reliability of me, the Christeller. As I mentioned, when the physicists got hold of this idea of atlases, they thought this was great. They wanted to make, for instance, an atlas of typical expansion chamber photographs modeled on a typical Röntgengram like the one I showed you by Grassi earlier. And they said that the way it worked was slightly different. For the pathologists and the anatomists and the other doctors and X-ray experts, you made a normal atlas, and then when somebody saw something that deviated from it, it was pathological. So I would show you these skulls. Grassi would show you these skulls. You would see what a normal skulls looked like in various representations. And then when you saw something that didn't look like that, you'd say, this person's sick. So the physicists had a slightly different idea. They said, we will train ourselves to recognize the usual, and then if something departs from that, it's a discovery. So the physicists used the normal and the pathological, to use Canguilhem's terms, in the opposite way, namely the normal became the routine and the pathological became the discovery and the new. And so every new image-making apparatus had versions of this. There were bubble chamber and so on. You would teach the scanners to recognize this is a pion, this is an electron, this is a proton, and so on. And then if you see something that doesn't look like that, ring the bell and call the next in command, and then that would go up the line of structure till it got to an Alvarez or somebody else like that who would authorize them to publish the paper at Berkeley and say, we have found a new resonance of the proton or whatever it was. Now, one of the things that you might think, and that I've tried to show is not the case by these examples, is that mechanical objectivity, this idea of a simple reproduction of what the world onto the page, was simply the result of the photograph. And that's absolutely not the case. That is to say, the photograph entered into this new way of seeing. It didn't cause it. And you can see that in two different ways, in two different directions. First, when they first took photographs, for instance, microphotographs, what did they do with those photographs? Did they reproduce them? No. They cut them, and they found the best part of several different ones, and they pasted them together. They made a Photoshop avant la lettre of their photography to produce an idealized microphotograph. So there was nothing commanding or causal about photography per se that caused it to produce this way of seeing. That was already there. The other is to say that the first instances of the mechanically objective were people like Funke, who simply drew what they saw. And they said, I'm drawing what I saw. And I'm even the optical deceptions. I'm drawing whatever's there. And so, but there are photographs. And when people start to use photographs, they often say they know that they have limited depth of field, they're slightly blurry, you can't get a student to recognize anything on them, unlike a good medical illustrator who draws in color with infinite depth of field and sharpness and makes the good things, the important parts stand out from the background. All of those things were possible, but people were willing to sacrifice all of that to have a photograph because they were trying to integrate the photograph into this campaign to form a mechanical form of sight. The authors have provided more realistic illustrations by substituting the surgeon's camera for the artist's brush. And the artistic intervention became, in the 19th century, mean, would have been unimaginable in the 18th century. I mean, why would you give up the great atlases by Vesalius and Albinus and Chazelden and so on? But they were absolutely willing to give them up for these not very great black and white photographs because the photographs seemed like a further step on the campaign to disengage the interpretation, the tendency we have to idealize, to make our theories be confirmed, to do all the things that Cajal accused Golgi of doing. And this was a way, it was participated in that. I don't think that technology drives this change. Technology participates in this change. And if you want to see how moralized this was, how this idea of creating the right kind of person for the job, the right kind of person to be a scientist, look at this remark of Rudolf Virchow. I am now, Virchow says, among the oldest professors of medicine. I have been teaching my science for more than 30 years. I have honestly worked on myself to do away with ever more of my subjective being and to steer myself ever more into objective waters. Nonetheless, I must openly confess that it has not been possible for me to desubjectivize myself entirely. With each year, I recognize yet again that in those places where I thought myself wholly objective, I have still held on to a large element of my subjective views, my opinions, my representations, my theory, my speculation. So this is what it would take. This is a job of self-transformation, one that has a kind of Schopenhauerian or almost religious cast to it, right? I mean, it's a sense of stripping yourself of that I want and allowing the world to speak through you, or allow the world to be seen, allow our sight to become a form of nature's sight, to allow that plant or that track or that crystal to be shown to the page with a minimum of interference, because we're always trying to interfere. And it is work to become this right kind of person to give mechanical objective depiction. So the second kind of sight limit, what does mechanical objectivity, we know what's good about it. It got rid of every Tom, Dick, and Harry who had their own private theory about the way the world should look and was squishing the skeletons into boxes that they shouldn't be in and breaking bones, so to speak, and moving things around to form the idealized images that happened to conform to what they wanted or expected, or what geometry they thought snowflakes should have, or what the form of tissue should be, or crystals should look like. But what's the downside of that, or what's the cost, what's the limit of that kind of sight? In mechanical sight, built through protocol-driven mechanical objectivity, we end up not seeing salient idealized forms, but also often we forego color, we forego depth of field, we forego precision, we forego pedagogical utility. These were filtered out, as it were, by epistemology, by the way we go about making knowledge, which is now going to be not drawing one arm of a snowflake and handing it to somebody else to reproduce 5 more times, by ontology, by the practices that go into producing these images, and by this new transformed self, the self that Virchow was aiming for. Back to the cartoon. We're now at the third stage, and we look again at this fourfold here of the scientific self, which now becomes an expert. What do I mean by an expert? I mean that we can be, we can become trained to recognize certain things and to do so in a way that's reproducible. It's not arbitrary. We can become, so we can learn how to separate different forms of electroencephalograms or cardiograms or star types from spectral images. We can learn how to make certain kinds of classifications, even if we don't know exactly the rules. We know how to carry on with doing it. And the image itself then becomes an interpreted one. That is and I'll show you what I mean in examples again, in which the image is not just, we don't just let the machine produce an image, because it was recognized that there were problems with that. And that if we simply reproduced onto the scientific journal page what came out of the machine with no intervention at all, we often get into enormous trouble, because machines produce artifacts, and we need to use the good sense and trained judgment that we acquire in the process of apprenticeship. And the practice then becomes one of conditioned judgment, of training, and the ontology that there are families of things that resemble each other, that if we actually truly represented every one of our skulls in X-ray form in a book, it would turn out that there's a huge variety. And how do you define where's the limit of natural variation and pathological variation? This was a problem that came out of this mechanical objective sight, because actually a lot of the things that we're interested in are not identical. They're not like Maxwell's molecules or bullets. And there's transitions here. For instance, Francis Galton had his famous composite portraits where he took all the murderers' pictures from London prisons and then superposed them and made a picture and said, this is what the ideal form of a murderer is. So what you have in that is a kind of hybrid of two forms of sight. On the one side, you have this mechanical procedure. You give me all the murderers, I line up the eyes, and then I print, if I've got 10 of them, I take a tenth of the right exposure time, and I print each for a second, say, and then I print it out, and I present you with Mr. Murderer, Mr. Platonic form of murder. So it was, on the one hand, an aspiration to form an ideal type, but to do so with a mechanical formation. So this is kind of a hybrid at the borderline of this transition in 1878. But interestingly, if you look at philosophers, and here I'm thinking of not just Wittgenstein, but Peirce and James and others, but if you look at philosophers in the early 20th century, you'll often see them beginning to grapple with the same problems as the scientists are grappling with. Here, Wittgenstein says, before he wrote the Philosophical Investigations, in a text on morals, I will put before you a number of more or less synonymous expressions. I want to produce the same sort of effect which Galton produced when he took a number of photographs of different faces on the same photographic plate in order to get the picture of the typical features they all had in common. I could make you see what is the typical, say, Chinese face. So if you look through the synonyms, which I will put before you, you will be able to see the characteristic features. Now, this is interesting on a lot of levels. One of them is that this idea that we know from Wittgenstein's later work of family resemblance actually is tied to facial aspects of the face as a model for the way we understand the resemblance of things. The second is the racialization of that facial depiction. And that racial metaphor that was used very often in work up till the catastrophes and genocide of World War II, all through the 30s and into the 40s, you'll see very often scientists using that language of facial racial similarity. For example, Gibbs and Gibbs were the great experts on electroencephalography, and they said, look, we have no protocols for telling you exactly how to distinguish different kinds of seizures, but we can teach you how to make that distinction. Give us 2 weeks of your time, I'll teach you how to make the distinction. And what they say is, where complex patterns must be analyzed, such subjective criteria are exceedingly serviceable. Although it is possible to tell an Eskimo from an Indian by the mathematical relationship between certain body measurements, the trained eye can make a great variety of such measurements at a glance, and one can often arrive at a better differentiation than can be obtained from mathematical indices. Accuracy, they say, should not be sacrificed to objectivity. Accuracy should not be sacrificed to objectivity. So this is a different choice of virtues for the scientist to pursue. Use accuracy, even if we don't have simple protocol mechanical rules for making the distinction. If we can all make the same distinction between a grand mal and petit mal seizure, it doesn't matter that we don't have a machine or a mathematical frequency analysis or Fourier transform that will tell us how to do it. Accuracy should not be sacrificed to objectivity. Analysis should be carried out as an intellectual rather than electromechanical function. The same thing you see in stars, where the spectra are published, and Morgan says in his book of the Atlas of Spectra, of stellar spectra, it is not necessary to make cephalic measures to identify a human face with certainty or establish the race to which it belongs. The observer himself is not always conscious of all the bases for his conclusion. the operation of spectral classification is similar. Good judgment is necessary whether the decision is made from general appearance or from more objective measures. So they're saying we need to inject some subjectivity into this. Our judgment is necessary to be able to make the kind of distinctions we want to distinguish stars, to classify life and death decisions of seizures. I mean, this becomes routine. And Baranowski, a surgeon, an atlas of surgical measures, says that his illustrator, Daisy Stillwell, was a superb interpreter. It would have been simple for her merely to act as a camera. It would have been simple for her to act as a camera. That was what everyone was trying to do in the 19th century. Now, he says, simple to act as a camera. That's not what I want my illustrator to do. Instead, she brought out the features that justified the picture. So this idea of judgment, over and over, even an atlas of the moon, you think, well, of course, we'll use photographs of the moon. We need to know what the moon, what the Mare Tranquillitatis looks like. This is the beginning of the moon program in the early 1960s, and the head guy in charge of Firsov, a guy in charge of the depiction of the moon for the astronauts, said, you can't just use photographs. There are variations of light and the reflectivity of different parts of the surface. You need to use good judgment and to draw the picture of the places you might want to land. So even when something as seemingly clear as the moon, you had to use judgment. In fact, in this Atlas of the Skull from 1965, these authors say if you actually just drew what you just simply saw, if you were just a machine-like illustrator, no one would ever be able to interpret it. You'd actually lose the location of the lesion that you were trying to recognize, and therefore to be able to help the patient. In fact, they said the natural had become the enemy of the realistic. The realistic depended on judgment, and judgment able to make more salient the things that were obscured in a simple naturalistic or mechanistic depiction. In this Atlas of Solar Magnetic Fields, the authors proudly say that they've added a certain subjectivity to these charts, because if they just reprinted what was coming out of the machine, no one would get any information out of it at all. There were just too many artifacts, but they had worked with this machine for years. They knew what was artifactual and what wasn't, and not because they were geniuses and sages and Goethe and Albinus, but because they were experienced workers with these kinds of measurements. And so you see a kind of shift from where people are saying, these are the terms that were used by the Atlas writers. They said you need to use some subjective elements as well as objective. You need an empirical art, not just an exact science. Sometimes we need unconscious classification procedures, not just conscious ones. We need a seeing eye, as they said, not just a reliance on indices, intellectual rather than electromechanical procedures, qualitative and not just quantitative, individual judgments, not just universal rules, and so on. In other words, in the apprenticed sight, in trained judgment sight, conditioned by expert judgment, we end up not seeing at all either the idealized forms of truth to nature or the mechanically reproduced images of mechanical objectivity. Elements, both raw and cooked, so to speak, were filtered out, as it were, by the strategies of gaining knowledge, by what we assumed there was out there, by the practices we used to get it, and by this new kind of trained judgment, the expert, scientific self. And I just want to gesture for a moment at where we've been headed more recently. In nanoscience, you have, in many aspects of the sciences today, from mathematics to physics, there are galleries. And these galleries include the older functions of these more classical atlases. And they include other things as well. There are, in one classification from South Carolina, they have the schematics, fantasy images like this one on the right is sort of a mini rocket ship repairing red blood cells that was on the cover of Nature. You have these documentation with false color, but that were based on real data. And then you have this artwork. So these works also function. This, for instance, this weird spooky looking happy face on the lower right was both used in a nanofabrication laboratory and also exhibited at the Museum of Modern Art in New York. So you have classical atlases, but now in electronic digital form of galaxies, of galaxies, of parts of the brain, of Calabi-Yau spaces. In fact, when you look in mathematics, you have not only books like this one, A Bestiary for Physicists of Calabi-Yau Manifolds, but also Calabi-Yau these spaces have their own homepage. And you can go to it and have it calculate things for you. So it becomes an interactive site, an atlas, but you no longer have a passive relationship to it. You also have things that might be thought of as virtual atlases. That is to say, meta-atlases like these heavily documented human forms, there's a male and there's a female, and atlases are made out of that. So it's a meta-atlas in the strict sense that you use it, and they invite you, the user, to make other atlases out of it by using coding colors and changing scales, and you can move your way through it. You can, as they say, make your own visible woman. An example of this, you click on it and you can, as they say, sort of drive your way through the body. So these techniques, these new digital techniques, have extended the form of atlas into other areas to use the computer and mediating idealization forms within the data itself. So you have a mixture of data that's coming from the atomic force microscope and computer-generated geometrical forms that help you identify the different facets of this adenovirus, for example. Or use of images on these galleries that are actually about intervention. They're actually about making things. So moving around a nanowire, for example, where you're actually using this to show how to make something, or as you're making it, to use it as part of the fabrication process itself. In that sense, sight becomes part of the instrument. It's not just the documentation of something. It's actually being used to make things, more like an engineer or a designer than the classical representation picture might lead you to expect. Here, this is from Rotemann's DNA origami, the piece that I showed you earlier that was in MoMA, and this is from the original scientific paper, or this picture that came out last month from Lieber's lab of a nanoprocessing and nanowires being used to make things, to make devices, and using the imaging as part of that process. And as these things move back and forth between a piece of research, the cover of Nature, and then this, for instance, Rick Heller's piece is sold in art galleries as a piece of scientific art, or a hybrid piece between art and science. So what do you have in this world? What you have is a scientific self that begins to combine, and this is just something that I think is emerging. I'm not saying this is all of science or even most of science, but you begin to see a scientific self in this world of engineered objects at the nanoscale that combines the ethos of the scientist, the entrepreneurial device engineer, and artistic authorship, that the image begins to combine aspects of simulation, intervention, mimesis, and analysis, that the practice is one of presentation, not so much representation or representation. It's not just documentation of what was there, it's actually part of the making process itself. And the ontology, it's not like these happy faces occupy our world and we discovered them. These are things that are designed. They're manufactured goods, you might say, rather than a specification of the already extant natural. So if you had to characterize the sight limits here, it may be that the instrument sight, this using a sight to actually make things, runs skew to the ontological and epistemological goals for the image that we've known for so long. It's not just, does this thing really exist that I've shown you a picture of? Like showing you a picture of a moon of Jupiter and saying, oh, look, this is something that I'm claiming is out there, and this photograph is evidence of it. Not, does it exist, or is our knowledge secure? The classic problems of representation, but instead with the engineer or designer, just the way the makers of the Brooklyn Bridge, don't worry, does the Brooklyn Bridge exist? They know it exists. The question is, will it have the strength to hold up under the tides and the weather and the people and things that are moved across it? And can it be made bigger in other places? Can you do this? So not so much does it exist or is our knowledge secure, but using images to help us see, can we make it robustly? Can we mass produce it? Can we make self-replicating entities, devices in the nanoscale? Can we make it aesthetically, economically, and politically? So that, I think that the image in these galleries is beginning to do something else. It's expanded beyond what we had in the day of the classical 19th or even 20th century atlas. So our idea of right depiction, what scientific depiction is about as we trace it across this sort of longue durée, keeps shifting. Not because it displaces the old. You can still see idealized bird drawings in many of the best bird guides, because that's actually the best way to learn how to recognize certain birds, not a photograph. But we also use mechanical objective representations like the atlas of the hand that prefers it over drawings of the hand. We have ones like the electroencephalograms that refer directly to the use of judgment. And we now have these new kinds of galleries that are showing us how to make things, and actually where the gallery itself is an object of construction. Make your own atlas, it cries out to you. This may be where we're headed next. Thank you. We have time for a few questions. So I gather we have time for some questions or thoughts. Yes?
Okay. Does your viewpoint on 1730 give any insight into why Isaac Newton spent time on metaphysics and alchemy?
Newton's is somewhat earlier, but I think your question seems right on the mark to me. Newton, so you might say, well, how could you say that Newton wasn't objective? I mean, Newton's depiction of the motion of the planets is pretty good, right? And the triumph of Newton in finding a universal law and giving science a whole new way of thinking about its aspirations was nonetheless not aimed in the first instance at removing him from in much of his work. Newton spent, by his own confession, much more time thinking about alchemy than he did about physics. And he kept hoping that the process of alchemy, the transformation of matter towards an ideal form, would give him insights into the world that nothing else could provide. He also spent an immense amount of time on theology with his anti-Trinitarian pursuits. Newton's a very complicated figure at a moment when mathematics he's extending and developing mathematics in very fundamental ways. But the goal wasn't to defeat, Newton's enemy was not to defeat idealization by the wrong sort of people, which was what the mechanical objective figures of the mid-19th century were. He had other ambitions that he was trying to get at. And to be able to strip away the artifacts and to be able to find a universal mathematical law that would cover everything from the tides of the Mediterranean to the moons of Jupiter was much more his idealized image of what science truly was revealed to be when you stripped away everything and got to its essence. So in that sense is much closer to this earlier form of idealized depiction. Emily.
As a historian of technology, I'm afraid I might try to put some sort of materialistic underpinning to the wonderful narrative that you just shared with us. But in thinking about these different eras, I'm thinking about the physical production and dissemination and availability of images as part of the story, and we clearly go from a kind of a handcrafted manuscript through, to print technologies and the printing of photographs to a digital era when all of us have access to every image that's, ever been produced almost instantaneously. And I wonder if you could just speak to that material aspect of image technology, what that contributes to your story.
Yeah, it's extremely important part of if you look at the way this story unfolds, a lot of it has to do with the technology itself, but it's the technology that participates in something. It's not that someone invents the photograph and so of course we want mechanical objectivity. So for example, when photographs like Worthington first had photographs of these shadow photographs and then later the dimensional photographs that actually showed the spatial representation of the splash, he had to draw them because they couldn't directly reproduce the photographs into the books. So one of the ways to think of this is that these effective idealizations, these idealizations, now I'm not talking about the idealizations of the scientists, but the aspirational goals of the scientists in, say, the 19th century as they were seeking to be able to make rigorous this idea of mechanical objective depiction, extended very much to the technologies of print. How could you get this to the page? For instance, how would you handle color when you had to? How do you standardize color in image reproduction? How do you move from a photograph to a reproduction of a photograph? And so a lot of attention, I didn't talk about this much, but a lot of attention was paid in the 18th, 19th, and the 20th century to ways of making the reproduction strategy in the book itself, or whatever medium it is, answer to the goals that you had for the right kind of depiction. So it's a very important part of the story, and I think it could be extended in the digital domain too. I mean, for example, in the images that correspond to the study of computational study of turbulence in fluids, one of the leading people in that area in France, Marie Farge, went back to in the 1970s and 80s, went back to the Bauhaus theorist Itten, his color theorist, and to try to understand the effects of different colors on their adjacent colors, and then designed a system of representation of liquid flow so that, first, that colorblind male scientists could still recognize what was going on in the pictures, and secondly, that the adjacent, she basically put a gray stripe between each of the layers of color so that they wouldn't interfere through adjacency effects of perception. So there was an attempt to use the materiality and the color materiality and what was known about color and color perception to depict things in a way that would be interpreted consistently by the reader. So a lot of the concerns all through this period, all through the 19th century and deep into the 20th century, was about making these objects useful to the people who were going to be reading them. So the reader enters into the story, and the medium is mediating, as media want to do, between the author-scientist or the author-scientist illustrator and the reader-user of these atlases. Yeah.
Resistance was coming from biologists and perhaps the adherents of the big science who felt that their funding was threatened, and the biologists who felt that their credibility as portrayers of species that were really out there was threatened. I wondered if you had any sense of who might or is resisting this four-part system that you're proposing.
You mean, who would not like the kind of manufactured goods?
No, the description, the conceptual description, because the biologists and big scientists didn't like the description, it seems to me.
Well, you know, if you start to list some of if you start to sort of think about the ways that science has been transformed over the last 2 decades, there are many. I mean, there's the enormous inversion of status and money that's occurred between the physical sciences and the biomedical sciences, where the biomedical sciences, in any measure or parameter that you can think of, overwhelms the physical sciences. Another is that the relationship between engineering and science has changed. And I think that the anxiety, which many of you will remember, I mean, if you've had any contact at all with physics departments over the last 10, 15, 20 years, is there was a period when physics departments would say, well, that's not physics, it's engineering. You don't hear that anymore. Or that's not physics, it's biology. I just, before this talk, just out of curiosity, in my department, at the physics department at Harvard, 20 of the 45 people or so list themselves in groups that are either theoretical or experimental physics and biology. So you have a categorical shift in many ways between the relationship, or among the relationship of this configuration of biology, the biological sciences, and widely construed, engineering and scientific engineering widely construed, and the physical sciences widely construed. It doesn't mean that every branch of each of these areas is making contact, but there are these, rather very substantial trading zones among them, where the work isn't simply classifiable as saying this is biology or this is physics, or this is engineering or this is physics. Just as in string theory, as this place exemplifies more than any place, you can say, I'm doing something and it's of significance, and whether it's stricto sensu physics or mathematics is not the most pressing question. The question is whether it's a fertile ground to plow. So I think that there has been, none of these transformations occurred without immense struggle. And it's not that it's completely over in some sense, or that it's engulfing. I'm gesturing towards something that I think is underway rather than completed. This is looking forward, not looking backwards from an endpoint. But the idea that engineering and physics, or engineering and chemistry, or engineering each of these dyads that I've spoken of has been the source of huge conflicts about hiring and about promotion and about the identity and what it meant to be a physicist, what it meant to be a biologist. You see in many universities, you go to a web page of somebody in the nanosciences, and you'll see that they're two. You can flip back and forth between a startup, venture capital, sort of outward-going proto-company, and a part that is, more classically integrated into the research zone. But there's a lot of overlap. It's often the same people, and the work is, the whole point is that the work is connected. But I think that this is a transformation really in the grounding understanding of what universities are about. And so it's very understandable that it's met with friction. I don't mean to say that people were being irrational in saying these things, but some of those struggles are now over. For example, the idea that you're not a physicist because you're doing biophysics, that debate's over. And I think that what we're looking at is, as these things begin to combine in the future, is a transformation in the nature of science that's really comparable to what happened in the years after World War II. I think it's a reconfiguration of the scientific disciplines with no other parallel in the 20th century.
Well, let me remind you that we can continue this discussion at a reception in Ford Hall, but before we do that, let's thank Peter Galison for a truly fascinating talk.